further ado, now that I've stressed how important it is to build these open standards and we need broader adoption of OpenCL, let me introduce you to Carol Herbst from Red Hat, who is working on an OpenCL implementation, which would be transforming the Linux desktop and laptops by providing OpenCL widely on Linux through the Mesa framework. And so Carol's talk today is Rusticl, Compute for the Linux Desktop. And Carol is GPU driver software engineer at Red Hat. Welcome, Carol, please.
Hi, everybody. Yes, thanks for being here. Compared to the machines most of the people here are working on, I'm working on very small machines like laptops or small desktop computers. So I've been a Mesa contributor since 2016. Mesa is like open source GPU implementation you usually use on a Linux desktop or laptop or whatever, and it's just, you know, GPU drivers for OpenGL and Vulkan and a couple of other APIs you use on, you know, normal Linux desktop applications. I started to work primarily on NVIDIA GPUs and OpenCL. When I was joining Red Hat, I'm kind of switching between doing GPU desktop things like OpenGL and Vulkan and OpenCL stuff. So it's kind of depends on what I'm working on at the moment. The first thing I actually worked on in the compute space was to provide an open user space implementation for shared virtual memory. And it actually implemented system level shared virtual memory in Mesa with the old OpenCL driver we had at the time. I wasn't really happy how this OpenCL driver was written, and it wasn't really reliable. So I started a new one a couple of years ago. And since then, I'm also participating in the OpenCL working group, helping out with various discussions or bringing up spec bugs because users find bugs. And I say, yeah, it's not an application bug, it's a bug in the specification. And having those kind of fun discussions, which I didn't anticipate on having when I was, you know, starting all of this. So what's actually like the current situation in the Linux desktop space in regards to compute? Sadly, it didn't have this kind of adoption you usually see in other places. There are a couple of workstation users of OpenCL and proprietary applications making heavy use of it. But generally, in the normal applications you are using, you won't see that much OpenCL or anything else, really. There's like a couple of applications, like, for example, Blender, but I will talk about this later. And there might be reasons for this, and maybe there was just never a good API or runtime providing compute to a wide range of GPUs. Maybe some of the runtimes were just a lot of packaging work. And if you are a little bit more aware of the Linux desktop space, you have like a lot of distributions and everybody kind of has to manage, you know, installing whatever OpenCL runtime the vendor is providing. And some of them are like really complex. Like if you know how complex like the Intel stack or the AMD stack is, it's a lot of work and a lot of people just don't do it. And maybe it's also like, what are actually alternatives to OpenCL? Maybe there are some, maybe they aren't viable, stuff like this. So here's a little small list of applications I think are relevant for the Linux desktop. I mean, there's a lot of OpenCL application outside this, but some of them, for example, OpenCV is also like a library which you can use for facial recognition, which has like also use cases in a Linux desktop. But there isn't really that much besides that. And I don't know if, you know, people generally just don't rely on OpenCL for their Linux desktop. Yeah. I have my thoughts on why this is the case. And what I think was the primarily reason is that we had an OpenCL implementation in MISA, but it wasn't really working well and it was AMD only. So for Linux desktop, it isn't really a good selling point if you say, yeah, I can accelerate this, but it actually only works on AMD. And most of the laptops are just Intel based. So didn't really make sense to actually rely on that. The ecosystem was also like pretty fragmented. So you didn't have like this one driver, which just works on every GPU, which we usually have with MISA. So it provides, MISA provides OpenGL and Vulkan of basically every GPU. And so we don't have that yet. Well, kind of, not really. There's also like a lot of people thinking, why even bother with OpenCL because it's dead. And that was kind of true 10 years ago or 5 years ago. But since then, I think a lot of people are investing more and more into OpenCL. And it's kind of cool to see. And yeah, the out of the box availability is just not there on the desktop. So if you have your random OpenCL implement, Linux distribution, maybe somebody has POCL pre-installed, but it's like CPU based. Maybe there's MISA, but that was in the past just AMD only, so you couldn't rely on it. So what were like the alternatives people could have considered? And before I can talk about it, I have to kind of explain what are the basic requirements a Linux desktop is needed for the desktop. So it basically has to run everywhere on every GPU, be it x86 based or ARM based or whatever. And a lot of people still have like GPUs from 15 years ago on a modern desktop, and I think it's pretty unfamiliar for a lot of people for you because I don't think you still have that old hardware, especially in supercomputers and stuff like this. So we still get bug reports about Firefox users getting crashes on 15 years ago or GPU like the GeForce 6000, which is super slow and everything, but people still use it. And app developers usually don't want to become like compute experts before like accelerating their, 10 lines of code to reduce power consumption or increase power efficiency. So the motivation to actually learn something new, which they aren't familiar with, is also pretty low generally. And they also want to use their favorite programming language. There are a lot of applications written in like C or C++ or Python or even Rust today, and a couple of others. So people obviously considered OpenGL for acceleration, which has some applications, but it's like the development on OpenGL is kind of stalled. It's pretty easy to use, but the compute capabilities are kind of low, and you are required to use GLSL. OpenGL kind of added SPIRV support in its latest version, but I don't think anybody uses it, and I wouldn't be surprised if it's broken everywhere. Maybe you know people who are aware of this, but kind of doubt it. Then there's obviously Vulkan, and it's pretty great because it has a lot of momentum, a lot of people adding new features to that. But it's kind of a super low level API, and people talked about it yesterday already, where app developers don't want to write 1,000 lines of code to just accelerate a memory copy somewhere. So it's really hard target for just accelerating parts of your application, and people generally want to use something much higher level than that. And the Rusticl, what I'm working on, actually also runs on top of Vulkan, so it provides an OpenCL implementation on top of it. SYCL has quite a momentum, as seen here on the conference, where a lot of people talk about SYCL and how great it is. and it's really actively developed. Sadly, it's not a one-time API. And the problem with that is that if you provide a Linux desktop, it has to run on every machine. So if you at compile time say, okay, but it only works on those GPUs, it's not an option. Adaptive CPP is fixing this. I think currently DPCPP doesn't have a generic target. Adaptive CPP has it. And I think once it's mature enough, I don't actually know how well it works. I just, look at the SYCL CTS and see a lot of tests being excluded for adaptive CPP. But if it's, if it's a usable state, no, it might make SYCL more interesting for the Linux desktop as well. Then there are like a couple of other alternatives like CUDA or whatever other vendor-specific language you have or API you have. But applications really don't want to rely all that much on vendor-specific APIs. And there are like applications like Blender, which is supporting CUDA and HIP, but that's usually the exception. And apps generally want to use some open standard like OpenGL, which a lot of GUI toolkits are using for acceleration. So this kind of brings us back to OpenCL because it's simple to use. I think it still inherited some of the times mindset. So one could say that the API is kind of outdated, but that's something which could be fixed. It's pretty abstracted from a programming model point of view. You generally don't deal with pointers directly unless you have a programming model like SVM, which provides you that. Spurry support is pretty great because this kind of removes the need to write the GPU code in OpenCL C. Currently, that's kind of the default, but through supporting an intermediate representation like Spurry, one could also write a Rust front end, which then compiles to Spurry. And I think with the LLVM backend or like the Spurry LLVM target, that might be what we are heading towards. So that would be cool to see. I also know people that who are working on getting other programming languages like ZIG compiled to Spurry, so that's also cool. So yeah, if we want to rely on some kind of compute API, kind of is OpenCL at the moment. So, but does it work out of the box? Sadly, the answer is still no. Some distributions started to package a lot of OpenCL runtimes. So they package the Intel one, they package the AMD one. But my goal with Rusticl is basically to have one runtime available or running on every GPU. So talking about the potential solution to the desktop, like compute desktop situation, Rusticl is a Rust-based OpenCL 3.0 implementation. It's using some MISA internal device abstraction API, so I don't have to actually write GPU specific code. It just we have a pretty generic abstraction which is used for like memory allocation and stuff like this. It's multi-threaded by default, which I think not many OpenCL runtimes generally are. So what's special is that I have a strict separation between the API validation, which happens on the application thread, and then the GPU submission, which happens on a separate background thread. So whatever you do on the application side, you don't actually have a high CPU overhead penalty for making sure that the GPU stays heavily utilized. So yeah, and it's basically my first Rust project. So I didn't really intend it to, this project to evolve in this way, but it kind of happened. So what we usually have at Red Hat is that we have like those days of learning where we can choose whatever topic we want to learn about. And I basically choose to, Rust was kind of getting attention, and I thought, yeah, maybe that's cool project, like cool programming language. And how I approached this was that maybe, because I was working on MISA, maybe we could use Rust there. And because I was also familiar with OpenCL and worked in this area, I was also like interested in, can Rust actually be used to implement those heavily C-based APIs? So what's really special and cool about Rust is that it actually removes entire classes of bugs. I don't know how many of you are, actually writing on driver code and C code and everything, but I actually never, I think it was like in the 3 years I had to use Volgrind or the address sanitizer one, like once to fix memory corruption bugs, and that's basically it. And it also provides a lot of cool interfaces to write thread-safe code, which I think personally have some advantages over how C++, for example, is doing things. So instead of mutex are really interesting, because instead of being some object you have besides your data, it just wraps the data, and every access to the data is actually protected, and you can't, for example, you can't forget to take a log. So that's really cool. So, but how does it actually look like? Or, the part of MISA which I'm actually caring about here is that we have a couple of front ends, which is like OpenGL or VideoPro and VA API, like video acceleration APIs. 9 is a DirectX 9 implementation, and Rusticl is like OpenCL, and the Gallium layer, like through the Gallium API, we are able to target a lot of different drivers. And the drivers here in questions are like Zinc, which is for Vulkan, and then Etna Weave is for the Vivanti GPUs, and a couple of others. It's already like a wide range of GPUs are kind of supported, or the work is in progress. VD3 is the driver for the Raspberry Pi GPUs. So I have a prototype for this, which kind of works. So OpenCL on Raspberry Pis is possible with Rusticl. There are just a couple of kernel bugs which we still have to figure out in the community. The compiler stack is also a little bit special compared to all the other OpenCL implementations, because the other implementations are basically LLVM forks and do whatever they want to do. But Rusticl is heavily SPIRV focused. So it uses the LLVM SPIRV translator for the OpenCL C code. The SPIRV ingestion is the fast path, so there's no translation happening to LLVM. And the OpenCL C path is actually also the exact same code path, just with a translation in front of it. We have our own internal IR, which is called NEAR, and it's used for common optimization paths, and some drivers are also using it for driver specific or like GPU specific optimization and lowering. And for like running on top of Vulkan through Zinc, it actually, like the NEAR gets translated to the Vulkan flavor of SPIRV. So that's already, everything handled this internally. So, but does Rusticl work out of the box? We still no. I have a an environment variable where users can enable their favorite drivers to run, and there are a lot of users who successfully run it. I'm a little bit concerned about enabling it by default, because when Clover was doing that, a lot of applications just checked like, oh, is it Clover? Then we just disable OpenCL support. And I didn't want to run into the same mistakes there. There are also like, our compiler isn't really handling complex kernel codes yet, because everything is inlined by default. And if you have a complex array tracer, then you get like SPIRVs with millions of SSA values, and you basically run out of memory. but it's really a rare exception and generally kind of runs well. And I'm considering enabling it by default soon. So, but what I specifically working on in the MESA community as well. So because the MESA compiler is not LLVM based, the compiler wasn't really capable of compute workloads because they are like different than the shader code you usually see through GLSL or OpenCL. So what we had to do is actually write a structureizer to translate the unstructured compute script you have to some kind of structure control flow shader or good GPU code. The support for pointers was also pretty bad at the time. So we actually had to do major reworks to the internal compiler to make this all work. Function calls is still something we have to figure out. As I said, everything is currently inline, but there has been work to actually support function calls and define some internal driver API for this kind of stuff. I was also working on advanced compute features like SVM. I'm still working on it, and it's a little bit complex, but we'll probably figure it out. So, but we also started to actually use OpenCL inside of MESA, which is something I haven't anticipated. To be clear, it's not the OpenCL runtime we are using. We are only using the OpenCL kernel language for internal GPU code. And we have a few ray tracers inside MESA, like the Intel Vulkan driver is using OpenCL to implement ray tracing. There are several shader stages. If you're familiar with 3D, if you're not, doesn't really matter. But they are like parts of the 3D pipeline hardware doesn't support. And a few drivers who are using OpenCL to implement those in software, like in software running on GPUs. And it's kind of cool to see this kind of things happening because there are like real advantages of doing that. Because you can basically share your code, what you have on the host side, where you have everything is written in C and you have your utilities and GPU register definition and stuff like this, and you can just share, like use the same code to also write GPU code for it. And there's like also pretty simple implementations of memcopy using OpenCL. Do I plan on working on other APIs supported inside MESA? Probably not, because for SYCL, we already have like other runtimes we just layer on top of OpenCL, which is kind of cool. For CUDA or HIP, we probably just will rely on Chipstar, which is also a cool project that was talked about before my talk. Level 0, we don't know yet what to do with that, because there's also like, I don't know if there's any momentum to actually use it for desktop applications, stuff like this. So what are my future plans with this? I think there are like a couple of things OpenCL should be working on, and it's like kind of my personal opinion on, having implemented basically the entire API, which are the aspects of OpenCL, which I find kind of interesting or a little bit annoying to implement. And the first thing I actually ran into were host pointers. I don't know if you're familiar with the implications of the spec basically saying you have to accept any host pointer, because GPUs don't really work that well with that, because you generally only can do this page aligned. So what drivers generally do is they just offset the pointer you have, and then you have more memory mapped into the GPU than you initially requested. So if you have memory before your host pointer, it might get overwritten by faulty GPU code and stuff like this. And there's basically no way to protect this. And OpenCL could say, okay, maybe you have to have some base alignment. You have to, align your pointer before you're able to use it. API validation can also be quite expensive, especially for desktop applications. What we have done for OpenGL is that we had a MISA, a MISA extension where applications could basically say disable all API validation. I think there have been some work for this to address in OpenCL, but I'm not aware, I don't actually know. But if somebody knows about some plan or want to talk about it, this would be pretty cool. There's also hard to figure out what's actually the optimal usage of the device I have. A lot of people, I think in the HPC area especially, they just fine-tune their code. But if you have a code base which should run on every GPU, you might need feedback from the runtime to tell you this code path is optimal and this code path might not be optimal. I'm also having a little bit trouble with the way multi-device support is working in OpenCL, and there's a lot of implicit data synchronization happening. And yeah, maybe it would be better to have it more explicitly, so the application developer actually knows what's going on, and not that much happens just behind the scenes, basically. Currently, the SVM USM situation is kind of weird because we have a lot of different APIs to basically do the same thing. Some are APIs more advanced, some are less. BDA is buffer device address for the one who are not familiar with the term. And I had some ideas because some of the Chipstar developers addressed me about how do we get pointers which are stable per CLMem object, and what you usually have in Vulkan or other APIs is that you basically can ask the runtime, give me this pointer of this memory allocation. And this also led me thinking about maybe OpenCL needs a different way of managing the VM of the GPU. What a lot of kernel drivers are currently moving towards is that the VM management actually happens in user space. So that means the user space can allocate memory, but it's ultimately up to user space at which address you place which memory object. And it might be a cool idea to have some API like that added to OpenCL as well, because it can actually enable interesting programming models where you don't have to track what memory object you want to use in the code, but you can just say you have this pointer and now you just back it up with a different memory allocation. Yeah. So I also have some thought about the ecosystem in generally, which I think some of you might have seen it, but I was filing a couple of spurious validation bugs for DPCPP. And I think that's something which I'm a little bit troubled with, that there's a lot of invalid spurious going on, and it's especially difficult for alternative runtimes to deal with them, because, for example, if you have DPCPP and you test it on your own runtime, and you just hand wave on validation errors and you just make it work, it would be more helpful if developers would ensure that the spurious they are generating is also valid to make it easier for everybody else. So I hope that people will be more careful about those things. Easier packaging is also something pretty important for the Linux desktop, because currently the most runtimes are really painful to get to the users. And I also kind of wished we had better debugging tools. I think there are a couple of vendor-specific tools which are kind of great, but I also would like to see more tools like the OpenCL intercept layer, which is pretty cool project actually to debug various applications or even driver bugs and figure out what's wrong. And I also have some thoughts on where I would like to see more compute happening in the desktop. Video encoding and decoding is some something which I was thinking about a lot. There's like always like this new video coding codec, which everybody thinks is cool and is new, cool and should be used. But this also means that old hardware not supporting it usually has to fall back to some CPU-based implementation, and those are pretty slow and drain your battery pretty quickly, or your laptop is running pretty hot and stuff like this. So this would be really cool to see. And there are also maybe some accessibility opportunities here. And I have to say, I'm totally not an expert in accessibility, but I talked with a few people who are familiar with the space, and maybe especially like AI, ML, maybe could be used to do more speech-to-text things, which I don't think exist in the sense of we have some CPU-based or like some CPU-based implementation to do that. Things like automatic picture descriptions, which is a problem in social media, especially because there are a lot of people who just don't care about this all that much. And if we could have some widely available compute API, maybe it would kind of solve this problem. So yeah, everybody should do this. Not everybody does. So it would be helpful if we have some tool for that. And the same goes also for summaries of long texts. Sure, there are a couple of tools, but they're usually not running on your own machine. So maybe we also need more higher level APIs, which are really focused on the use case. AI ML kind of seeing this. Apple also did a few things in this regard where they have, they are not really exposing or advertising OpenCL or to use Metal directly for a highly specialized use case, but they have also a couple of specific APIs for various things. So what I really like is the focus on Spiri. And I think, as I said before, if you are able to use whatever programming language you want and you can translate it to Spiri, it could make compute adaptation way higher. If you can use whatever you want to use. And what's also like, what I would like to see changed is that, for example, the official HIP implementation or OpenMP in general, they target GPU-specific ISRs. And for the HPC use case, that's perfectly fine. But for the desktop, we really want some GPU-independent target. And the GPU is just different thing, and it shouldn't be part of some compile time decision. But because maybe your application is 10 years old and you still want to have it accelerated on your modern GPU, and that's why I think that Spiri should become the de facto compute IR going forward, which I think we are heading there already. So that's cool. There are also a couple of other considerations. Some laptops really have really slow GPUs. If your AI ML thing is using needing a lot of processing power, if you rely on that for accessibility features, it's kind of not great if you need a beefy GPU to be, have an accessible system. Unified memory is also often slow. The GPUs you usually deal with have like discrete memory and is super fast. But on your normal x86 laptop, it's pretty slow. Apple luckily solved this. So if you run compute workloads on your MacBook or whatever, it's decently fast compared to what you usually see on Intel laptops. So, any questions?
Is there a role for OpenCL?
The question again?
In the list of applications, I noticed that things like Blender were just not there. What about
Blender doesn't have OpenCL support.
They removed it.
They removed it.
I'm out of date. Okay.
Yeah, they have CUDA and HIP, and I think I would like to use the support Blender through Chipstar and to use it on top of OpenCL. Oh, really? Is it upstream?
Yeah.
Since when? Okay, but it's fairly new, right? Okay, yeah, maybe I haven't checked for a year then. But yeah, if SYCL is supported, then yeah, that's also cool.
If people want to try Rusticl, how do they start?
Within the documentation. No, it kind of depends on your distribution, but usually there's an OpenCL package. And there's this Rusticl enable environmental variable you can use, and it's described in the documentation. There's like, can I use a web browser? Yeah. So yeah, with something like this, Iris is the driver for the Intel GPUs. There's like, can I even read this? It doesn't. But yeah, you can use it. Look it up at the MISA environmental variables documentation, and yeah.
At the beginning of your slide, you say that SYCL, the problem is like what happened is hard to package because maybe people would run on a system without any backend provided by SYCL. I guess if you develop a portable OpenCL implementation, in theory, you can package a SYCL implementation with an OpenCL backend, right?
Yes. So DPCPP would be viable to use on top of OpenCL if you have an OpenCL runtime, or like OpenCL as supported on all the GPUs. But there are still like users who use the NVIDIA proprietary driver, for example, and they would, I mean, they could still like use OpenCL, but maybe the CUDA path is faster and stuff like this. So.
I see. Thank you.
Thank you, Carol, for the great presentation. I had a different kind of question. We're talking a lot about Rusts everywhere. Would you have any advice for any person wanting to try Rust on one of their projects?
I mean, I think basically my advice is to just try it out. There are like tools like bindgen or cbindgen where you can actually just get your C functions available to Rust. It also kind of depends on your build system, how easy it is to integrate Rust. And in MISA, we use the Meson build system, and there's some helpers to make it easier to use bindgen. So you can just say, okay, I have my header files. Those define all the C functions I actually care about. And it generates, a Rust library you can just use in your Rust project and, integrate it into your current build system. If you want to write an application from scratch, they're usually using Cargo, and there's some documentation on how to use it. But if you want to replace things bit by bit, then you usually need to use the bindgen or cbindgen to, integrate your current code with the new Rust code.
Thank you. And second question. If you have a SPIR-V backend in an LVM and you have your portable OpenCL implementation, are you going to bring GPU compute to Rust?
I was thinking about this, but I don't know if I have the time for this. But yeah, I think it would be cool to be able to write GPU code inside Rust and make use of the Rust memory safety features also on the GPU side. But I'm not really familiar with adding support for this to a programming language. But yeah, I think it would be a wonderful project. People want to look into this, bring, essentially make more programming languages support an LVM to output Sprue. That would be really cool, actually.
Thank you.
Hi, thank you for the presentation. About writing this tool in Rust, when you were like going deep, how many or what percentage of your code was just unsafe Rust?
Maybe 1%.
Okay, great.
There's like, there's a couple of wrappers which are just wrapping around C functions. The actual advantage we have is that I'm not wrapping an external library. So I can just say, okay, we guarantee that the safety properties are fulfilled and just hand wave on the entire thing. What I also usually do is that the OpenCL specification is giving you guarantees. Like it says you have to pass in valid memory and stuff like this. And I just say, okay, it's valid memory because, if you don't do it, then your application is broken anyway. So there's like those things going on, but like, you don't really have to use all that much unsafe code if you are not targeting GPUs directly, I think. And it's pretty high level in a couple of places.
Okay, thank you.